Let's go ahead and start out our advanced math by looking at factoring and solving quadratics. So factoring polynomials is just the fact of rewriting them in what we call a factored form, where we have some smaller polynomials, often binomials or single terms, being multiplied together, such as x squared plus 3x plus 2 can be rewritten as x plus 1 and x plus 2. Now, one of the big things that we want to keep in mind is we always want to check for a GCF first. If there's no GCF, or once we do find a GCF, then we can continue to factor using one of several methods. Here's some general guidelines for when we have 2, 3, or 4 terms and how we can factor. I'm going to go through each of these as part of the examples. I do just want to note that if we have 2 terms, you're going to need to know these special case formulas as well as one other that I will show you so that you can quickly and efficiently factor these types of polynomials. So let's start with our first polynomial. We first want to identify, is there a GCF? Since there's no GCF, then we can just go straight into factoring. And we look and we see we have a trinomial. Now trinomials are typically factored where we are looking for a product that gives me my C value that also has a sum of my B value. So A is our leading coefficient, B is the linear term, and C is the constant. And so we want 2 numbers that multiply to give me a -10, but also add to give me a 9. So the 2 numbers that achieve that, well, that's going to be a 10 and a -1. Now when we have no leading coefficient on our polynomial, those 2 values just become our 2 factors. So we'll have x plus or minus some number, and then we'll have x plus or minus the other number. This is our most basic factoring, and so the sign, the plus or minus, will be based off of the sign of the numbers that we choose here. So we have x plus 10 and x minus 1. And again, the commutative property applies, so you can write these factors in any order. They will still be equivalent. Let's go ahead and take a look at B. When we look at B, we do see that we have a GCF, a greatest common factor, of 3. So we can actually divide all 3 of these terms by 3 in order to factor out that greatest common factor. And then we can go ahead and continue to factor. We'll see that this is actually the same as the polynomial we have above, so we already know the rest of the factors, x plus 10 and x minus 1. Now on C, we notice that we have a leading coefficient, but there is no greatest common factor. And so we're going to factor the trinomial just a little bit differently. Instead of just a product of C, we're going to look for a product of A times C. So we're going to do 2 times -5. We still want a sum that gives us B, which in this case is 9. I don't know why I wrote -5, -10. There we go. Now you'll notice that those are the same values that we had over here, which means we're going to be using the numbers 10 and -1 again. But what we do with those numbers is going to be different because of the leading coefficient. Those won't be our factors, but instead we're going to take the middle term, the linear term, and split it into 2 terms with 10 and -1. So we'll rewrite the equation as 2x squared, write that a little bit neater, if it would write, try again, there we go, 2x squared, and we're going to split 9x into 10x and -1x minus 5. So we split the term, 9x, into those 2 terms. Now we're going to do a method called factor by grouping. Factor by grouping works when we have 4 terms, 1, 2, 3, and 4. And what we're going to do is we're going to split the polynomial in half, and then we're going to factor a GCF out of both pairs of numbers. So the GCF for the first 2 terms is 2x, and when we factor that 2x out, we're left with x plus 5. Then we're going to go ahead and factor a GCF out of the second two terms. Now the goal here is for us to be left with the same thing in parentheses, x plus 5, that we had over here. So we think, what can I factor out? That leaves me with this result. We can factor out a -1. So now that we have this split, what we have now is two terms that have another common factor. These two terms now have a common factor of x plus 5. So we can factor out x plus 5 as a whole chunk as a GCF, and when we factor it out of these two terms, we're left with 2x, 1 as our other two factors. And there's our solution. We'll go ahead and do the same thing with D. We're going to find the product of A times C. So 6 times -3 is -18. And we need a sum of B, which is -7. So the two numbers that do that, -9 and 2. So we'll go ahead and split -7x into those two terms. 6x squared minus 9x plus 7x, plus 2x, 2 minus 3. We'll split it in half. We'll factor out our GCF for each pair. 3x gives us 2x minus 3. Now this last pair already has 2x minus 3, so we need to factor out something that doesn't change its value, such as a 1. One of our factors is the common binomial. The other factor is the coefficient that we have left. Now we look at E. E doesn't have a GCF. We can do A times C just like we did before, but I want you to notice something special about E. When we look at the first two terms, 4x squared and 9 are perfect squares, meaning we can take the square root of both of them and we get integer and nice simple values. Well, when we have perfect squares, we should test something in our trinomial. We can take the square root of both of those terms. We get 2x and we get 3. If we multiply those together and then multiply it by 2, if we get the same value as our middle term, then we have a special polynomial called a perfect square trinomial. And perfect square trinomials always follow the same factoring pattern. If we have a starting and an ending term squared, and our middle term is 2 times the product of their square roots, as long as the last sign is addition, the first sign can be either plus or addition, or plus or addition or subtraction, it will always factor to be the same type of case. The square root of the first term, the square root of the last term, plus or minus matching this sign above, as a binomial squared. So since we know that this matches the case of a perfect square trinomial, we can take the square roots, match the sign in the middle, and write it as a binomial squared. 2x plus 3 squared. Now with f, we have only two terms, and again we have something special where these are both perfect squares. So the difference of squares is one of our special cases where it always factors a plus b and a minus b, where a and b are the square roots of the terms. So the square root of 9y squared is, 9y to the fourth, and then the square root of 25x squared is 5x. So we're going to have two terms, or two binomials with those two terms, one with a plus sign and one with a minus sign. So now let's look at a little bit more analytical problem. If we have 8x squared minus 5x minus 22, and it's factored to equal those two given binomials, a and b are constants, we want to find the value of a minus b. So we could look at how we could factor this, and just until we get enough information, as long as we know the pattern of the factoring, it could be a lot faster than doing the entire problem. So one approach is that we can go ahead and start trying to factor. So we look at the product of a times c, 8 times negative 22, which equals negative 176, and a sum of negative 5. The two numbers that achieve this are negative 16 and 11. So we'll split this number into negative 16 and 11. 8x squared minus 16x plus 11x minus 22. And we can start factor by grouping. 8x leaves us with x minus 2. And we actually have enough information now. So think about it without having to factor all the way through. We know that this binomial has to be one of our factors because we'll make it happen on the other side as well. And it matches up with this binomial that we have here. And since those match, we know that b has to equal 1 because that's the coefficient here, and that's what b needs to be here for those to be the same. The second thing we can notice is that this is the first term of our second factor, which means that it has to be the first term of the other factor given here. So we know that 8x equals ax, therefore a has to equal 8. So we now have enough information to evaluate a minus b. It's 8 minus 1, which equals 7. And now we'll go ahead and finish up by looking at our special case factoring. So we looked at it a little bit already. We saw we had a perfect square trinomial, a difference of squares, and then we also have sum and difference of cubes, which is a different factoring formula, but the idea is the same. So how can we utilize this special factoring to make our life easier? So we're given two equations with their values and something that is not in a factored form. But if we analyze these really closely, we can see that this is a difference of squares, and this is a perfect square trinomial. So when we have the perfect square trinomial and the difference of squares, we can go ahead and factor them by using the patterns. X plus y, x minus y for the difference of squares, and then x minus y squared for the perfect square trinomial. And then since these are completely factored and these match up with the expressions that we have here, then we know that x plus y has to equal 8, x minus y has to equal 2, and then we have 2 squared, and we can multiply these all together. So 8 times 2 to the third power, which is 8 times 8, which gives us a value of 64. Then here again, we're just factoring, utilizing our answer options to our advantage. Again, noticing that we have some perfect squares here, and see, well, does this make a perfect square trinomial? Well, 2x times 7 doubled equals 28x. So yes, we have a perfect square trinomial, which means it's just going to be these two roots with a plus sign, quantity squared. The answer option that makes that work is D. And then lastly, here we have two terms, so we know it has to be a difference of squares or a sum of difference of cubes, but neither of those values are perfect squares, and 8 is the only part that is a perfect cube. But we have to remember that we can always factor out a GCF first. We have a GCF of 2x, leaving us with x to the 4th minus 4, which is a difference of squares, but also note there's only one answer option that has the GCF that's correct. This one has the wrong GCF. So we know that this has to be our answer option, and we can quickly verify it by comparing x squared minus x to the 4th minus 4 is x squared plus 2, x squared minus 2, using our difference of squares formula.